Hello Newtonians! In this video, we are going to learn about projection methods on engineering drawings. We are going to look at why projection methods are important, and we will learn about pictorial drawing projections like perspective, oblique, and axonometric projections. Furthermore, we are going to look into orthographic drawing projections and see what the first and third angle projection method means and what the difference is. In the end, we will look into the auxiliary views. Think about the glass of wine. It is quite a simple object. It has a curved liquid container, bowl, a pillar for holding the glass, stem, and a stabilizing area below the pillar, base. Now, how would you visually represent it to someone and explain it? Without the defined set of rules, it is impossible for the mechanical design engineer to communicate his design intent for other people to understand it and manufacture it. Today, using CAD software for mechanical design became the industry standard. Using CAD software, we can easily derive any projection or view that we need. The real knowledge is to know what projection we need and why. Like any other software, the CAD software is smart as much as a person using it. Types of the engineering drawing projections. We can divide projection methods into two main groups, pictorial and orthographic projections. An object's pictorial projections give a three-dimensional representation, 3D, on a two-dimensional plane, paper. They are not providing the specifics about the object, but they are providing visualization. We can divide them into perspective, oblique, and axonometric projections. Furthermore, the axonometric projection can be divided into a trimetric projection, dimetric projection, and isometric projection. An object's orthographic projections give a two-dimensional representation, 2D, on a two-dimensional plane, paper. Working with orthographic projections, we specify object features to the point where an object can be manufactured. We can divide the orthographic projection into the first angle projection, preferred in Europe, and the third angle projection, preferred in the USA. Pictorial drawing projections. Perspective projection. The perspective projection represents the true view of any object. It represents the object in the same manner as the human eye would see it. As in real life, depending on the station point, i.e., the eye, and the object's position in regard to the horizon, we can see that object appears to converge in one point, the vanishing point, and we can see the one, two, or three sides of an observed object. The perspective projection is rarely used in engineering drawings. Even though we can easily create it with CAD software, usually, isometric projection is shown on the drawing. However, as perspective represents the true view of any object, it is handy to use it for product visualization. Sometimes, it makes sense to put things into perspective. No pun intended. Oblique projection. The oblique projection lets the viewer see the most descriptive view as a front view in true size and shape. The most descriptive view is parallelly projected to the plane of the paper while the rest of the object is distorted. Most of the time, the oblique projections are drawn at an angle of 45 degrees or 50 degrees. Oblique projection is rarely used in engineering drawings, but they are beneficial for quick sketches, concept generation, and product visualization. Axonometric projection. The axonometric projection is similar to the perspective projection except that there is no vanishing point. The object can be placed at any orientation with respect to the viewer. The axonometric projection can be divided into three groups, trimetric, dimetric, and isometric projection. The trimetric projection provides an infinite number of possible projections. On this projection, the angles alpha and beta are not equal, and the same goes for the sides AB not equal AC, and AC not equal AD. In the dimetric projection according to ISO 5456-3/1996, alpha equals 7 degrees and beta equals 42 degrees, AB equals AC, AC not equal to AD. In the isometric projection according to ISO 5456-3/1996, alpha equals beta equals 30 degrees, AB equals AC, AC equals AD. The isometric projection is most used on engineering drawings to show a 3D representation of an object. Exploded view. The exploded view illustrates the relationships between different components that form an assembly. In other words, the exploded view shows how various components are put together to form the assembly. The exploded view shows the assembly disassembled rather than showing the part completely assembled. This type of view is usually used in parts catalogs, user manuals, work instructions, assembly instructions, etc. The assembly components in exploded view are shown in the same axonometric projection, usually isometric projection. Therefore, the most important aspect of creating the exploded view is to choose the view direction that shows as many components as possible. Often, centerlines are used to show a connection between the cylindrical components, and thin solid lines are used to show a connection between the non-cylindrical components. These lines are referred to as connection lines or trails. It is also worth mentioning that depending on the purpose of the exploded view, we can add component identification using balloons. Orthographic drawing projections. The orthographic projection is the holy grail of the engineering drawing. It is in the center of every drawing, and it is used for specifying the 3D object to the point that the object is manufacturable. In orthographic projection, the face of the 3D object is always parallel to the 2D plane, paper. This means that the face that is projected is true, there is no distortion of the object's face. There are 6 such views for any 3D object. The main view, or a front view, is always the view that is the most informative, i.e., it gives the most details about the 3D object. The number of additional views, sections, and detailed views should be limited to what is necessary to fully define the object's dimensions. On the engineering drawing, we are using either a first-angle projection or a third-angle projection. In both projection types, views are the same, but the position of the views with respect to each other differs. The rules for creating these projections are defined by ISO 5456-2-1996. First-angle projection. In the first-angle projection, the object is positioned between the observer and the projection plane. Every view is projected perpendicular through the object to the projection plane, i.e., the shape of the surface is parallel to the projection plane. Considering that we have 6 orthographical views, the projection planes of all views form a cube, and the inner faces bear the projected view. The first-angle projection is preferred in Europe. The symbol for the first-angle projection is defined according to ISO 5456-2-1996. Third-angle projection. In the third-angle projection, the object is positioned behind the projection plane. Every view is projected perpendicular through the object to the projection plane, i.e., the shape of the surface is parallel to the projection plane. Considering that we have 6 orthographical views, the projection planes of all views form a cube, and the inner faces bear the projected view. The third-angle projection is preferred in the USA. The symbol for the first-angle projection is defined according to ISO 5456-2-1996. Comparison between the first-angle and third-angle projection. If you wonder why the first and third-angle projections are named as they are, there is quite a logical explanation for their names. It is connected to geometry. When the object is placed in the first quadrant and is projected to the plane, we get the first-angle view arrangement. When the object is placed in the third quadrant and is projected to the plane, we get the third-angle view arrangement. Projection lines. Now that you understand how orthographic views are created, the last step to fully understanding the topic is understanding the interconnection between the 6 views. The object's height in the front view equals the object's height in the left, right, and back views. The object's length in the front views equals the object's length in the top, bottom, and back views. The object's width in the top view equals the object's width in the left, right, and bottom view. During your studies, professors may ask you to create projection lines on your drawing. That is probably to ensure that you understand the matter. On the other hand, you will never use projection lines on your drawings in actual engineering praxis. This would only make the drawing more complicated and messy. Usually, your orthographic view on engineering drawing will look like this. Auxiliary views. Previously we discussed the 6 main orthographic views. As we now know, the shape of the object's surface is parallel to the projection plane. But what if we have a surface that is not parallel to the projection plane? When we have a surface that is not parallel to the main projection plane, that surface projected to the main projection plane is distorted, i.e., it does not show the surface's real representation. In that case, we call this surface foreshortened or shorter than the true length. In order to show the true shape of the inclined surface, we can use the view called auxiliary view. The auxiliary view shows the true size and shape of the inclined surface. It is created in the way that the surface is projected onto the projection plane that is parallel to the inclined surface that we want to show. The projection lines are used in the same way as on the main views. On the drawing, it will be present without the projection lines. Instead, the direction line will be introduced to show the direction of the view and the identification with a capital letter. Usually, On the drawing before the capital letter, I would add the remark view. When you have a large number of sections and detailed views, I believe that it is easier and faster for a manufacturer to read the drawing. The projection methods are something that you will encounter whenever you create a drawing. The better your understanding of these methods is, your accuracy and speed of creating drawings will increase. Therefore, it is worthwhile for your career to practice using these methods. Did you learn anything new in this video? Let us know in the comments below. Do you like our videos? Then, give us a thumb up, comment, and share it with your friends, colleagues, and on your social media channels. And if you want to become a part of the Newtonians, make sure to subscribe to our channel.